Welcome to this afternoon session for the lab for Physics4C. Today is April 5th. We are going to talk about lab, I forgot the numbers now, I think lab 7 or something. It's on heat engines. This lab is very, very important for you guys so that you know it's important in terms of preparing actually for the exam too. Because it has several, we're doing this stuff online, so we really can't do much about it. If we were in class, we would have several heat engines where you guys explore the idea to determine if it's heat or not, if it is, heat engine that is. If it is, then explain it basically. But at this point, there were two questions from the lab that I had to skip because of that. So we're doing simulation. Even in the actual lab, when we do it in class, we still give these calculations, and they're actually very handy in the sense that they help you prepare for the exam so that you know how to calculate everything related to the energy associated, related to the work, which is very important for an engine, related to the heat that has been basically extracted from the hot source, and the heat that was dumped to the cold source, and also in terms of the entropy calculations for this cycles. So you go through all of the steps doing the calculations, and hopefully you will learn from them how to do actual problems basically related to homework problems. These engines are not realistic engines. They are actually three processes engines. In a sense, you will only have three processes, okay, where you calculate these quantities, basically everything up and above, okay. In general, as a rule of thumb, the area between that is enclosed in the cycle itself is what is the work in this case, okay? In the standard notation, and I made a big fuss over this one, is actually a negative number if you go clockwise, which is exactly what the engine is supposed to be. If you go counterclockwise, it will turn out to be a positive number in the sense that you really have to supply that energy. It's energy added to the system. However, we're going to follow the convention of the book in this particular one, where the integral for a clockwise direction for an engine still is going to be positive, indicating that work has been delivered, work is done by the engine, okay? Whereas if we're doing a heat pump or a refrigerator, is going to be opposite to that. In a sense, you're going to find the value being negative. That means it's work done against the gas. So that is really the only thing that I have to really be cautioning you from it, because of the fact that you might get confused a little bit, especially with the literature out there is dominant in the sense that the definition of the work in this case is minus PDV and not plus PDV. And the first law of thermodynamics in that way is the change in the energy of a system is the amount of heat added plus the work done against the gas. Okay, so that is Q plus W. In this book, they use Q minus W to compensate for the fact that the definition has W in it with a positive PDV, basically, dW, that is. So this is, in a sense, the only thing, and I made a big fuss over it. So when you are actually in an exam time, as long as you're clear exactly what you're doing, whether you use this convention or the other, you know exactly what's happening in here, that this is an engine, is going through a clockwise cycle, then in this case, the amount of work delivered will be whatever you find from there, W, the area of that cycle, basically, or the amount of energy lost in the form of work is the same thing as that area. So that is the same verbiage, the same language. So if you do that, I'm not too worried about it. Again, you're supposed to pick up two engines from the 8 that are in the instructions and deliver all of the answers, and I will show you the table basically that you guys have to fill for each and every one of those, okay? At least the 2 that you're gonna pick. It's up to you. Which 2 you're going to do, it's up to you. However, that doesn't mean it's free for all, basically, because you are supposed to understand all of the cycles. So if you do 2, you're supposed to look at the other 6, basically, and see how you're going to calculate them. That's why it's very important to be part of your review for the exam, to go through all of these 8 engines to understand exactly how they work. I mean, provided that they are not realistic, they are some sort of a basically a theoretical, if you wish, engines, but that's basically what we're basing this off of. The rubric is on Canvas. So I'm hoping that you guys will go through the rubric. Again, the lab is not due as it says it is due. Let me change this since I remember I mentioned that earlier in the day. Okay, let me edit this. I'm just changing the date when this lab is due. So it's not going to be due on the 10th, which is this weekend. It's not going to be due on the 17th, which is the spring break. And it's not going to be due actually on the 24th, which is actually where the midterm exams is. It's going to be due all the way to May 1st, okay? So I hope that you will have ample of time to submit this thing in time. But that's just for the submission, okay? When you're supposed to submit the lab report. I'm going to be reminding you again after the exam about this date, okay? I already changed it in the system so that it shows that it's due on May 1st, okay? Doesn't show me that. Yeah, it's due May 1st at 11 p.m. Okay, so that fixes that. So please do not, first of all, it's part of your review of the exam, so you're supposed to finish it anyway, finish at least the activities. And after the exam, after the midterm, I'm going to send you a reminder about it again so that you guys submit it in time so that you don't lose points. And hopefully you take care of all of the assignments that are due, because I'm planning on spending the some of my time on the spring break to prepare you guys for to at least grade some of the stuff that is not graded, okay? So this is in terms of the logistics of this exam. There is a rubric, like usual, and you will see that the actual doing is worth a lot of points. So you really have to actually do these things. So let me find, first of all, where my lab instructions are. And actually, it's in here. So let me share with you, where is share? The heat engines. Okay, so again, this is the theory and the background information, your name and the name of the people. This is a time where you are supposed to really work with your teammates. This is a time when you pick up somebody and work with him or her and divide the tasks. You work on this engine, I work on this engine, but you are still working together on it. This is actually critical to basically work together. That's why I require 2 engines, because you're going to see 8 of them. You're going to discuss it hopefully with a partner and decide, you know what, I like engine 2 and engine 7. What do you think? And then he says or she says, maybe engine 7 is not too great. Maybe let's do 8. 2 and 8 sound good. That is a discussion that I want to see. And because you would want to come up with different ideas, because you would want to explore all of them before you actually decide on which ones to submit. And once you submit it, it's a good idea to have somebody else to reflect upon. Now, if you have difficulty with the calculation or have problems with it, please let me know, so that I don't want you to get stuck with it. I want you to really progress. This is not an exam. This is part of the activities you're supposed to do to learn. Again, you're supposed to go through the background information and how heat engines were discovered a long time ago, first of all, and then they were actually revised back in the mid 1800s, and then after that they will come up with a formulation for them. This is in a nutshell what a heat engine is. Extracts energy in the form of heat from a hot source and dump the excess heat into the cold source. In doing so, it's going to do work for you, okay? This is the typical numbers that we're going to be working with throughout this lab. The temperature T-cold, it's about 27 degrees Celsius, which is roughly room temperature. We're rounding it to 300 Kelvin. And the T-hot in this case, usually it's a boiling point or slightly more than the boiling point of water, which is the boiling point is 373. So we're going to use 400 Kelvin for T-hot. So those are the 2 temperatures we're going to be using with. And again, the volume changes roughly basically around 1,000 cubic centimeter, okay? And if you do the conversions properly between the atmosphere, this is the atmosphere 101,000 pascals, or 1 atmosphere. So you can convert it to pascals. And a Pascal is actually Newton per meter squared, force per unit area. If you multiply force by meter, it's going to be energy in joules. So it's joules divided by an area times meter, which is meter cubed. So if you do this conversion, you're going to find that convert the meter to a centimeter. So you're going to find that at the end, another convenient unit for the pressure is going to be joules per cubic centimeter. So this is the number that we're going to be operating with. This is actually normal room temperature, normal room pressure. So this is the Pmin that we're going to be working with. This is the temperature for the hot engine, T hot, around a little over the boiling temperature of water. And this is about the room temperature, which is the temperature for the T cold. Okay, so those are some of the numbers. Here they are summarized. Okay, the baseline, the pressure is going to be about 1 atmospheric pressure, which is this many joules per cubic centimeter, 0.1. The volume is the maximum volume is going to be around 1,000 cubic centimeter. And the temperatures for T hot and T cold, you're going to see them as 400 and 300. Sometimes I don't mention those numbers, but you're going to assume that this is true for all of the 8 engines that you're going to have in this lab, that this is TC and T hot. Okay. It's very important when you're doing problems, especially in the exam or the midterm, when you're dealing with engines, that these temperatures are in Kelvin, not in degrees Celsius. So if you're asked for the efficiency and they tell you the engine is operating between 20 degrees Celsius and 100 degrees Celsius, the efficiency is not 20 over 100. No, it's 20 plus 70, 273 divided by 100 divided by plus 273. So that ratio of the temperature has to be in Kelvin, not in any other unit. Again, I mentioned briefly the fact that going clockwise is an engine. Okay, if you follow the convention for the area, this is going to be a negative area. Okay, because when you go clockwise, this area is going to be negative. The book, though, takes it, the negative of the negative takes it positive, takes it an absolute value, if you wish. That is the work that is delivered in this case by the engine. If it is a heat pump or refrigerator or AC unit, obviously it's going to be counterclockwise. And if you integrate an area over counterclockwise, it's going to be positive. But the book then will have to take it negative in that situation, because of the fact it says that, okay, you're supplying energy to in the form of work, you're compressing the gas or something like that. That is basically what happened in that case. So it's going to take it negative, which is kind of counter the convention. But for this lab, we're sticking with the convention for the book because we want to compare apples to apples, so that you guys, when you go and look at the formulas, you know what's going on. As a word of caution, I already mentioned that before, today and before, that you have to have it clear in your mind what's going on. Clockwise direction, with which this is the PV diagram, by the way, this is V and this is pressure, is an engine. So it's delivering work, it's doing work, okay? And the work is this shaded area, this area that has this grayed area, if you wish, okay? That is the work in this case. Obviously, it doesn't matter where you start from, but the highest temperature in this point in here will be the asymptote somewhere to this graph. Obviously, this is T hot and this is T cold. Had this been a Carnot cycle, it may or may not, this is not actually a Carnot cycle. Had it been a Carnot cycle, its efficiency would be 1 minus TC over T hot. But this does not look like anywhere near anything that we can tell. But it's still an engine. Okay, at some point we're getting Q hot, which is Q in, and this is Q out, which is being dumped to the cold source. And the efficiency is going to be the difference between the two, which is the work in absolute value, divided by the amount of heat that you have to pay for. This is basically the amount of heat that you have to do, okay? Again, you can find the pressure because this is through a pressure picture. This is the ratio of the maximum pressure to the minimum pressure. This is the compression ratio between the minimum volume and the high volume in a cylinder, for example, if you are thinking of a piston. And again, you can find actually the adiabats in this case, and the adiabats will give you where the maximum in here, The entropy, you have reached it in an extreme fashion in this case, okay? So you can really do an analysis with that one. Here is what I was cautioning about, okay? The work is that integral over the entire closed path, okay? And it's the sum of all of these integrals, if you can find all of these integrals through the entire path, through a closed path. The way the book does it and the way this lab does it, it has a plus in here. Otherwise, in normal textbooks and normal standards, there is a minus in there. The minus indicating that energy being delivered, lost in the form of work, because the gas has to deliver that energy through an entire cycle. This must come from somewhere, it's not coming from the gas. Obviously, in the case of an engine, it's being supplied all the time by a chemical reaction somewhere, okay? So that is to close the cycle so that you can go back and close the cycle. Otherwise, deliver the work for you once and that's it. And that's not a useful engine. So you would want the engine to go again and again and again and again and again and again. So that takes you for a long time. So again, this is why where there's an issue in there, okay? This is the definition of W net. W net is the positive value that is the difference between the Q hot and the Q cold. In this way, we're taking absolute values. This formula takes absolute values, okay? In general, it's an algebraic sum, where one of them is positive, the other one is negative. So in this case, we took care of that. The energy change is always NCB delta T. That's why in an isothermal process, delta T is 0. Delta T doesn't change in an isothermal process. So delta U is 0. In an isothermal process, there is no change in the internal energy of the gas because the temperature doesn't change, okay? CV now depends on what type of gas we're dealing with. If it's a monoatomic gas, it's actually equal to 3/2 of an R. If it's a diatomic gas, it's 5/2 of an R. If it's a polyatomic gas, it's 7/2 of an R, okay? Or roughly that number, okay? So obviously, what was I lost my points in here. Okay, R is a known value. This is how much it is. So this is coming from the ideal gas law, PV equal to nRT. This is what you have seen in chemistry, and you have seen it in this class. Here is what my point is. Writing it this way, where is it? This way for the work with a positive sign in here, you would have to compensate for it somehow. In this book and in this lab, we use the minus in here. I know it doesn't sound symmetrical between work and heat. It seems like one of work and heat, yes. And that is really not good because it looks like you have to add something and subtract the other one. But in general, if we take the definition, redefine W with the proper sign in here and indicating that if it's negative, like in this case, which is negative, it should have, at least it's going to come out negative if we had the proper sign. It's going to come out positive if we follow their convention. Then in this case, you don't have to worry about it again. You just have to define it with a plus sign in here, and that's it. And there will be symmetrical behavior. You add heat to the gas, its energy will go up. You do work against the gas or compress it, its energy will still go up. So you define it once and you don't worry about it. Then if you do the opposite, you're just going to get the negative sign for the energy. The energy will go down. If you remove heat from it, its energy will go down. Its temperature will go down. If you have it do work, then its energy also will go down. Okay. In the case of the isothermal, you're doing both actually. In the case of the isothermal process, when delta T is equal to 0, you're actually having it heated up and then doing work. So you're raising its energy through heat, but also lowering it by having it do work. Both of them, they will be just the right amount so that they cancel each other. So that is what an isothermal process is, okay? And efficiency is defined by what you want, which is work from the engine, versus what it costs you. And what it costs you is that heat that is being extracted from the hot source. This is actually a waste. Q out is being wasted. But it's necessary to close a cycle. Without it, you're not going to have actually an engine. Okay? So you have to waste some of that energy. That's why the efficiency is always less than 1, because this amount divided by that one is always less than 1. So that's in a sense why we frame the second law sometimes is, I mean, the first law, the energy, they add up exactly. W net plus Q out is equal to Qn. So the first law is perfect in here. It's well 100% satisfied, regardless of what type of scenario you have in here. But it is the second law that messes up things for you. You could, theoretically, you could think of this way. If Q out is 0, then all the heat you get from the heat source will go to work. So this is a 100% perfect system where there is no losses in it, okay? Where everything will behave correctly in a sense that all the heat taken in is converted to work. That is the ideal situation, but that doesn't work because of the second law. Second law requires that there is a Q out, okay? There is waste in here. So with the first law, the best thing you can do is break even in a sense that W net will be equal to Qn. The second law will actually dash that hope in a sense that you cannot even do that because the W net will always be less than Qn. And that is how the efficiency is defined. In this lab, we're going to use the symbol epsilon for the efficiency. So it's going to be W net over Qn, assuming all of these quantities are positive. The efficiency is always positive. And it's usually written as a percentage. If you do this ratio, it's going to be a decimal point. Usually there is the assumption you're going to multiply it by 100% to get it into decimal points, to get it into a percentage representation, okay? So these are the processes we learned about, the isothermal process. The isothermal process, the temperature is constant. So it's come out of the integral, and you'll all be left with the dV over V, and the dV over V is just the ln of the ratio of the volumes, okay? And this is basically, in a nutshell, summary of what we did. This is why I like this lab, because you guys will have a summary of a lot of things that we learned so far, okay? We have the isothermal process. T is constant, delta U is 0. The heat is nRT ln of the ratio of the max volume over the min volume. The way they define this W in work in the book is also W and Q is equal to 0. But remember, the delta U in this case is just the difference between the two. Since those two quantities are equal, then the difference between them is 0. Delta S in this situation, the change in the entropy is just delta Q over T. And T is fixed. It doesn't change in an isothermal process. So in this case, it's the T cancels from this expression, and you will be left with NR, the natural log. This is not the log in the base 10, by the way. This is the natural log. So do not use the natural. So do not use the log in the base 10. Okay. So this is basically here is an item. Please put it in your notes in here. Do not use the log in the base 10 or any other log in this calculations. All of these logs are in natural logs. Otherwise, you get wrong answers all over the place, especially for the exam, which means that for the exam, you have to bring a calculator with you, and that calculator better be able to do natural logs because you will need it. Okay, you will need that calculator. Please make sure it's fully charged. You don't want to come to the room and then you turn it on and nothing comes out. So make sure it has batteries, brand new batteries, or fully charged if it needs to be charged, okay? So that is something that you will need for the exam. Again, I will send you reminders for what you need more in the exam, other than a pencil. And you will need a pencil for sure, and you will need a calculator. You do not bring with you scratch paper. I'll provide that. You do not bring with you formula sheet. I will provide that for you. I don't want you guys to memorize formulas. That is not the subject of this class at all. So I'll give you all the formulas you will need. And if you think that you need something that was not given, and formulas including physics formulas, and including some integrals that are well known, and integrating also the trig functions if you guys need trig functions, or trig identities also if you need trig identities. And if you think you need something else during the exam, let's say, for example, hey, what is the formula for so-and-so? There are two ways to answer that. Either I tell you, okay, you really don't, you could, it's part of the problem. This is something that you should work on your own for it. Or if it is something that you actually need, I will go to the board and write the formula for everybody so that everybody will benefit from it, not just you. Does this make sense? And how we're going to handle this exam thing?
Yeah.
I don't want, very good. I don't want you guys to memorize anything in here, but I want you to understand it though.
So,
Yes, we're going to.
question. So those logs should be changed to ln's then, right?
Yes, when all of these calculations, these are natural logs, ln's.
Okay.
Okay. All of this chapters. We have never seen the log in base 10 at all in this class. All of these logs are natural logs. Anyway, this is the isovolumetric process or the isochoric process. This is at constant volume. So in this case, we know W is 0. Remember, W has to do with the dV. So if dV is 0, I don't know. Can I do it this way? No, this way? I don't know how to do that right now. I lost track of it, okay? I want to, it's going very slow in here on this scrolling thing in here. And I don't want to use the mouse because if I click on the mouse, it's going to probably take me to the next few pages. I mean, the clicky thing. Okay. So in an isovolumetric process, W is 0, which means that delta U and delta Q are the same. And this is true regardless because which way you define the work. It's going to be 0. So in this case, it's NCV delta T for the heat. This is constant volume. So this is specific heat, the molar specific heat at constant volume. And this exactly is going to be the delta U. Delta U is always true. Delta U is always this quantity. The only reason why it's 0 in here is because delta T is 0. That's all. There is no change in temperature. So as you can clearly see, delta U is always given by that expression. In here, delta Q is the one that changes on U. Now it's delta C, NCV delta T because there is no work. Here, it's NCP delta T. This is heat, the molar specific heat at constant pressure. But still, delta U is still NCV delta T. Okay? In this case, it's an adiabatic process. I'm sorry, in the adiabatic process, there is no heat exchange in an adiabatic process. This is how we defined it, actually. The energy is still NCV delta T. So that means that, because of the way they define this stuff in here, that the work is going to be minus NCV delta T. That's all. The entropy you divide by T in here, but in here you have to integrate this expression for Q, dQ over T, integrated from an initial temperature to a higher temperature. So it's going to be NCV, the natural log of the ratio of the two temperatures. In here, you're going to integrate dQ over T. So there's going to be dt over T integrated from some initial temperature to a higher temperature. So it's going to be NCP, the natural log of TH over TC. And in here, the work is going to be simply P delta V because the pressure is constant. In this case, the pressure is constant. So when you integrate P dV, it's just going to pull P out. So it's going to be the final volume minus the initial volume. And if you write PV equal to nRT for both sides, it's going to be nR times delta T. This is why, if we rewrite this expression, NCV delta T is going to be NCP delta T minus nR delta T. That is how we found that Cp equal to R plus Cv. The relationship between Cp and Cv always is coming from this expression. In this case, because Q is 0, there is no heat. By the way, this is a bad notation, okay? I think I should fix this one next time. I thought to do it this time and I forgot. You cannot say delta Q. You cannot say delta U. You can say Q and you can say the W. Sorry for that, okay? But a small step, yes, you might call it dQ, dW. But overall, it's W from one starting point to another point, okay, on a certain path. Same thing with the Q from a starting point to another point on a certain path on the PV diagram. But delta U is 100% justified because you have an energy at some point and you have new energy at some point. So the change in the energy makes sense. The change in the entropy also makes sense because both of them are state variables. However, Q and W are not state variables. Therefore, you say how much heat was added, Q, and how much work was done, W. End of the story, okay? Depending if one of them is positive or negative, heat removed then, or work done against. That's the story, basically, in a nutshell. Sorry for that, okay? Please fix that in your reports and make sure they understand the distinction between S and U as state variables, with also T and V and P as state variables, whereas W and Q are not state variables. You cannot say change in heat. Doesn't make sense. Okay. How much heat did you have before? Now this is how much heat you have now. No. That's nonsense. Okay. Tell how much heat was added or removed, end of story. Because it's just a transition value. Same thing with W. It's transition value between 2 points on the PV diagram. Okay. Again, isovolumetric or isochoric process. So that's the second process. And this is basically, we went through the analysis for it. Here is the gamma. Gamma is defined as Cp over Cv, okay, by definition. And it's a dimensionless number. In the case of a monoatomic gas, it's 5 over 3, because you have an atom that is a point particle in space, like the case of the helium, which is monoatomic gas, can have a kinetic energy in the x-axis, the y-axis, and the z-axis. So it has 3 degrees of freedom, and that's what that 3 is. Cp is always Cv plus R, okay? So this number plus R, divide the two by themselves, you're going to find 5 over 3. In this case, it's actually in addition to the x and y and the z direction for the molecule to move in the case of a diatomic gas like the carbon monoxide or what is it? Oxygen, which is in the air, O2, or nitrogen, N2, or carbon monoxide, not dioxide. Carbon dioxide is actually of this type. It's a polyatomic gas, okay? Or nitrite oxide, NO, also is a diatomic gas. So all of these guys, they have this property, so you can use this for gamma. Like I said in the lecture, most of the times when we're dealing with combustion and in engines, we use this value because of the fact the main component of the gas is actually the air, okay? So that is really why we use this value for the most part. And then we have now the definition Cp over Cv. This is how Cv is in terms of gamma, because R is constant. This is how Cp is in terms of gamma, okay? Okay, why can't I see this stuff in here? Show, no, show. Can I reset? No. Okay, I think now I have, that's what I wanted to see. Full view page. Okay, good. Now I can jump from page to page. Okay, good. So the isobaric process, is this, can you see this thing or is it too small?
Can you zoom in a little or?
Okay. You guys should have it actually part of your
You're right. I have it open.
Okay, very good. So please follow through, okay, and make sure you have notes in there. The reason why I don't like it this way is because it takes a long time for me to, let me quickly, yeah, actually, here's the point that I want to go through. The isobaric process is here, and it gives you still the stuff that we did actually in lecture, and we arrived to this nice formula for Cp and Cv, okay? And if I go zoom out, zoom plus, control plus, control plus, control plus, okay, good enough. So this is the expression that you will need to do some of the calculations that you will need for your, if I know Cv, I can find Cp because R is constant, 8.314, okay? How are we doing on time? I'm going slow on this one for a purpose, okay? And it's going to, we're going to go into more detail. So the adiabatic process is a process where there is no heat exchange by definition. Q is equal to 0. So delta U is equal to minus W in their notation. In either case, it's minus PDV, that is fine, okay? Integrated. So we're going to go through the integration and come up with this expression for it. P V to the power gamma is constant. So P initial times V initial to the power gamma is equal to P final times V final to the power gamma. And that was the previous lab, actually, that we did on the adiabatic process. So this is actually similar to that. Gamma is always greater than 1, no matter what. Okay, because it's always, if you go back into equation 6, you will see that it is equation 6. If I divide by Cv in here, I will have gamma equals to 1 plus R over CV. CV and gamma and all of them are positive. So that's why gamma is always more than 1, no matter what you do. So that is basically what we have in here. So now question 1. Using equation 6, which is basically says Cp is equal to Cv plus R. And the definition for gamma show the following. So basically, if you go back into that expression, you're going to find Cp equal to Cv plus R. You divide by Cv, and you're going to say Cp over Cv, which is gamma, is equal to 1 plus R over Cv. Solve this equation for Cv. Moving 1 to the other side is going to be gamma minus 1 is equal to R over Cv. Flipping the whole term gives you Cv equals to R over gamma minus 1. So you're going to show this expression, okay? And also, once you find what Cv is, all you have to do is multiply it by gamma, because remember, gamma is equal to Cp over Cv, so Cp is gamma Cv. So whatever Cv is, you're going to multiply to get what that Cp is. In other words, if you know what gamma is, you know what Cv and Cp are, okay? So if you have an exam or something and gamma is given to you, so from that point on, you know exactly what Cv and Cp are, okay? Because Cv is R over gamma minus 1 and Cp is gamma times R over Cv minus 1. I'm sorry, gamma minus 1. Okay, so this is the Carnot engine. We did that in lecture. Okay, we did it today. So these are the important steps in it. You have an isothermal, followed by an adiabatic, followed by another isothermal, back with an adiabatic to the starting point, and you have the cycle now going clockwise in this fashion. And you can pull the relationship on the isothermal, and on the other isothermal, this is at constant T cold, this is at T hot, and you're going to put the relationships for the adiabatic, on this adiabat, P min V max to the power gamma, P beta times V beta, because the convention in here is you have these names in here. Okay, so this is the PV diagram for an Carnot cycle. Okay, so this is the maximum pressure with the minimum volume. This is the maximum volume with the minimum pressure. And these are values in between them. This is a TH, this is an isothermal. This is a TC, this is an adiabatic. I mean, in the other isothermal. And this is the adiabatic, no heat exchange. And this is the other adiabatic with no heat exchange either. So this is constant entropy, and this is constant entropy. Entropy doesn't change. So that's why we call these processes isentropic processes, okay? And if we follow the calculations, this is the story. In the first stage, the temperature doesn't change, so delta U is 0. In the second stage, there is an expansion from V beta to V max, okay? And there is an expansion from T hot in temperature to T cold. So in this case, there is a change in the entropy, which is NCV times delta T, okay? In other words, sorry, where is the, why am I looking at this process in here? No, forget about this one. We need to focus just on this line in here. T cold, here. This cycle, we're going this way, from this point to this point. So delta U is 0. In this case, the heat is coming this way, and it's going to be minus RTC ln of Vmax over this volume, V alpha. The reason why you have a minus in here, because technically it's the V final over V initial. So we're going in a compression from the volume V max to V alpha, and the pressure is going from P min all the way to P alpha. So it's going up. So in this case, if we follow the previous table, it's going to be in RTC, in nRTC, the temperature is T cold, and the final volume, which is V alpha over V max. But because we're flipping the volume and the ratio in here, because this the ratio, the initial ratio was less than 1. So if I flip it V max over V alpha, and this is a natural log, not the log in base 10, you're going to get, in this case, a minus in here. and the energy is negative in this case. The heat is negative in this case because we're dumping heat during this thing in here. The work, by their definition, the way that they have defined it, also is going to be a negative value in here, okay? Because the work and the heat will be 0 because delta U is 0 in this case. Does delta U is equal to delta Q minus delta W? Obviously, if you subtract this number from that number, delta W is subtracted from delta Q, you're going to get 0. So yes, this is a guide for the rest of the lab and how you fill it, okay? The entropy now. Entropy in this stage in here. This is at constant entropy from alpha, V alpha to V min, okay? There is no change in the entropy in this case, okay? So we are going through this stage, and this is the adiabat. In this case, delta U is changing the temperature from T cold to T hot, okay? And the delta U is NCV delta T. There is no heat during an adiabatic process, so Q is 0 in this case. And the work then must be equal to the negative of delta U, because delta U is equal to minus delta W, okay? Is it true that 0 minus this number is equal to that? Yes, because 0 minus minus is going to be positive, and I have this answer in here for delta U. So this is the second process. The third process in the cycle is a TH going from V min, P max to V beta, P beta. So in this case, the temperature is not changing, so we're back to delta U is equal to 0. And if I do the formula again, nRTH ln of V final, which is V beta over V min, okay? So this is the expression that we have in here for the heat. The work is going to be exactly the same quantity in here. We're going to get the same expression in here, which is just the integral of PDV, okay? Without the minus, the way that this book and this lab defines it, just to follow through. The difference between Q and W is identically 0, so yes, this checks, okay? S max, we're going now through this adiabatic expansion, going from V beta to V max. Pressure is dropping from P beta to P min. So in this case, the delta U is equal to minus dW, okay? Delta U is always NCV the delta T. T final, which TC minus T initial, okay? In this case, which is higher than this temperature, T hot, okay? So delta T in this case all the time is T hot minus T cold. So it's going to be minus this whole thing times T hot minus T cold. The work is going to be simply, if we follow the calculation in here, is going to be NCV delta T. Is it true that 0 minus this number is equal to this number? Obviously, yes, okay? Is it true that U net is 0? So you add 0 plus this number plus 0 plus this number. Is it true that 0? And obviously it is, according to this numbers that I have in here, okay? So yes, it checks. The total energy is 0. Starting from one point, which was this one, going through the entire cycle and coming back to it, yes, there is no change in the energy of the gas. Okay, this is the network. The network is the sum of all of these quantities basically in here, okay? This one and that one, they cancel. So it's going to be end up with nRTH times the log of V beta over V min minus nRTC ln of this number. Because these two quantities are the same, so they cancel. So when you add the network, you're going to find dW net. That is the area inside this graph. That is this area, okay? So you add this quantities only. So that is the work, okay? Qn, the hot, that is the heat that is coming in through T hot, is this much. Q out is this much. The efficiency, which is W net over Qn, turn out to be, because when you do the calculation in this cycle, T hot over minus TC over T hot. Okay, the question in here, is it true that W net is equal to Qn minus Q out? Let's check it. Is it true that W net is equal to Qn, which is this quantity, minus Q out, which is that quantity? Yes, it is. Okay. This is theoretical. Okay. So for the entire lab, you're going to go through this process again and again and again and again and again and again until you get it all mastered. Okay. Okay. So this is a Carnot cycle. And this is the proofs for it and so on and so forth. Okay. Now, given the data, if you take V min to be 200 cubic centimeters, use equation to solve for the values of listed above. So you have V min to be 200 cubic centimeters, and you're going to find everything else because you know what the temperatures are from the previous table in here. So you have the temperatures being 400, this temperature being 300 Kelvin, and the Vmax is 1,000 cubic centimeters, and this one is being 200. So you're going to plug in all of the numbers, okay? All of the numbers. So if you're trying to curious, for example, trying to find n, because you will need n, you have the pressure in here. What is the pressure in here? PV equal to nRT, okay? And you have the temperature in here, and P max, V max. You have all of this things in the table, so you should be able to get the values in here, okay? You have 1,000 times this pressure, which is what? This is 0.2, so this is 1, 2, 3, 4. So this is 0.04, and this is 0.06, okay? Or is it? No, this is, okay, find the divisions in here in this graph. Okay, let me blow it up for you guys to see it. You can use a ruler in here to find it. So this is 0.1. So this is 0.1, okay? The pressure is 0.1. I'm sorry, that's what we said in the beginning. And the units in the pressure in here are in joules per cubic centimeters, as we said in the beginning of the lab. So this is 0.1. So we know what the pressure is. We know what the Vmax is. Vmax is 1,000 cubic centimeters. And this pressure, now you can find it based on the calculations. You can find the number of moles. Since you know 200 centimeters cubes in here, you know the number of moles from this point, you should be able to do the calculations in here. If you have difficulty with it, please do not get stuck on it. Please let me know and we should be able to get this thing done, okay? We have a lot of things to do, so we're going to continue. This is the auto engine that we did first before actually doing the Carnot cycle, Carnot engine. All of this relationship, we did them in class today. This are with high entropy, this is with the low entropy, this is an adiabatic, this is an adiabatic process. These are two isochoric processes. And this is basically how the Otto cycle look like. So if we follow the calculations, we're going to get this results again. During the delta U, during the S min, it's always NCV times the difference in temperatures. So S min, it's we're going through this cycle again clockwise. So during this stage from this point to this point in here, we have NCV times the final temperature T alpha minus the initial temperature, which is TC. T alpha minus TC times NCV. There is no heat exchange in this case because of the fact we're going through an isothermal. I mean adiabatic, I'm sorry, okay? So Q is equal to 0. So this case, delta U must be equal to minus the delta W, or minus W. Again, I'm sorry about this delta in here, and that is associated with Q. It should be just Q and W. Is it true that delta U is equal to Q minus W in this case? The first law of thermodynamics, yes. You subtract this from that and you're going to end up with 0. Okay? Sorry, 0 minus this number, 0 minus minus, so it's going to be positive, so you're going to find delta U. Okay? So follow the same thing as before. For the process, the isochoric process from T alpha to T hot. So in this case, it's going to be NCV times the final temperature minus the initial temperature. In this case, it's at constant volume, so it's NCV T alpha minus TH. And since it's a constant volume, there is no work in here. So this number minus 0 is going to be that number. And then for the S max, it's the opposite of this one, except it's going from a temperature to T beta to T hot. It's actually from T hot to T beta. It's actually this cycle. From T beta to T cold in this case. I'm sorry. I'm sorry, from T alpha T hot to T beta, you're right. So it's going to be this S max. It's final minus initial. This is 0. This is NCV, similar to the first process, except now happening at 2 different temperatures. And if you take C 0 minus minus, so it's going to be the same thing. And this is the last stage of this process, from T beta back to TC. NCV times that. There is no change in volume, therefore there is no work. And this is going to be Q. So W, delta W is equal to Q. Q minus 0 is going to be same thing as W. Can you add these numbers in here and verify that this is equal to 0? Obviously, it should be. T alpha minus T alpha is 0, cancels. T cold minus T cold cancels because this one is negative and that is positive. T beta minus T beta cancels. TH minus TH cancels. So if I add all of these numbers, they give me 0, as it should be, because I'm going through a cycle, starting from this point all the way coming back to it. So there is no change in the energy. How about the network? This number plus 0 plus this number plus 0. So it's going to be NCV times TH plus TC minus T alpha minus T. So the 2 minuses by themselves, and I'm sorry, there is a minus times minus. So you add up the numbers and you're going to find that one. Qn, this is Qn, a Qn in here actually, because this is happening at higher temperature, and this is the Q out. Okay. So if you do all of the, oh no, I'm sorry, this is the Q out. And this is the Q in. Okay. Again, this is the Q in, and this is the Q out. Okay. Is it true? So if you check these two expressions, Q in minus Q out, you should be able to find exactly that this is true. I'm sorry, yeah. Okay. You should be able to find that this expression makes sense to you. Okay. We saw this one. They use rho in this case. Okay. We used R. Just another variation. So the ratio of the two volumes between this volume, 1000 to 200, that is what R is. So 1000 divided by 200, R is equal to 5 in this case. Or rho is equal to 5 in this case. Okay. So rho is equal to 5. And so that is the efficiency, 1 over 1 minus 5 to the power 1 minus gamma. So it's going to be to negative 0.4. So you have to be careful in here because it's really 1 over R to the power gamma minus 1. Okay, so that's what that expression is. So instead of writing it to the power gamma minus 1, you can write it this way. Okay, 1 minus gamma, except now put the R in the numerator. Okay. So this is how we're defining rho, which is how we defined it R in the class. Okay, anyway, use these equations to show that T alpha is equal to TC. We did that in lecture today, actually. So you can go back and refer to the lecture and answer question 3. And now they give you numbers now. Actually, Vmax in this question is not 1,000, but 1,200. 1,200 divided by 200, that is 6. So you're going to be having an efficiency of 1 minus 1 over 6 to the power 0.4. Because gamma is, no. What value of gamma should be for this engine? The Otto engine is an internal combustion engine that burns the inside of the cylinder. What value of gamma should be for this engine, given that the table 1, that Vmin and Vmax, which is the efficiency of this Otto engine? Okay, so we need more numbers in here. Oh, we have T alpha, we have TC, we have a lot of the numbers in here. So we can find what this efficiency is actually, because we can find what the W net is. We can find what the Qn is. Once we find what the efficiency is, we're going to just solve this equation for gamma, basically, okay? So let me, how are we doing on time? Man, it's already an hour. Okay, again, let me share with you the screen quickly here. And let me, yeah. Okay, so let me stop sharing that screen just to make sure that you guys understand how to do this calculation quickly. So this is what the deal is. You can find epsilon basically from one problem, which is just the W net, which you can find divided by the Qn, because you have all of the data in here for this problem. The only thing you have to remember in here, Vmax is not 1,000, but rather it's 1,200. cubic centimeter, okay? And Vn is 200 cubic centimeter. And you can go through the temperature. T hot is 400 Kelvin, and T cold is actually equal to 300 Kelvin. Okay, having said that, now you should be able to find the gamma, because this ratio is also equal to 1 minus 1 over, the way that is defined in this book in here is rho, at least in this lab, over gamma minus 1. So what we're saying in here is solve this equation for gamma. So this is how this would work. So you move gamma to the other side, it's 1 minus epsilon. Epsilon now you cannot use a percentage, it's going to be a decimal point, is equal to 1 over rho to the power gamma minus 1. That means that rho to the power gamma minus 1 is equal to 1 over 1 minus epsilon, okay? It's going to be more than 1, this number, when you do it, because this one is less than 1. So 1 minus number less than 1, the whole ratio, this number is going to be less than 1, but when you take the ratio, it's going to be more than 1. In other words, gamma minus 1 is going to be ln of 1 over 1 minus epsilon. And this whole thing is going to be positive. Again, because this is less than 1, when you subtract 1 from less than 1 from a 1, it's going to be less than 1. 1 over a number that's less than 1 is going to be more than 1. So this is going to be more than 1 when you do the calculation. I mean, positive, I should say, not negative, positive. Not necessarily more than 1, but positive for sure. So gamma is going to be just 1 plus the natural log of 1 over 1 minus gamma minus epsilon, or if you really care about it, it's going to be 1 minus ln of 1 minus epsilon. And again, this is a positive number with a minus in it. Otherwise, this number is negative, and times the negative is going to be positive. So this number gamma is going to be more than 1, as it should, okay? And you should be able to find it. Since we can find the efficiency from one way, which is the network divided by the Qn, then we're going to sub that value in here and solve for it and find gamma. So this is the answer to that question, but of course you need to do the calculation with it. So that's question 4. This is the activity that was removed. If you go through the rubric, that you will see that there are missing questions 5 and 6 from the grading, because, and I left it in there because I just want to come back to it in the future, just in case if we go back to class and I can do this lab, okay? This is the instruction now, and I'm going to go through this one in detail on what you need to do. So we're going to pick up 2 engines, okay? Actually 2, not 3, okay? Each works with a fictitious engine, and you're going to be working with it. So, question 10. The second law of thermodynamics says that no heat engine can be 100%. Do you observe this for the 3 engines? So it's only 2 in here, okay? So we're going to do it for the 2 engines. That's they are required. If you choose to do more, which is you're encouraged to because of the exam, please do so. And you should be seeing an efficiency that should be less than 100%. So that question 7, you cannot really do it until you do this activity. So this is an engine number 1. Engine number 1, doesn't matter where you start from this point, for example, on an isobaric process. You go from Vmax down to Vmin, then from Vmin, at the same pressure, at the same volume, you go from Pmin to Pmax, and then you go through an isothermal. When you see temperature TH in here constant, that is an isothermal. So this is an engine 1. So what is given to you? You're given Vmax. You're given T hot. You're given T cold, which is this temperature at this point. You're given also Pmin, this pressure. You're also given gamma. Obviously, tau, which is just the ratio of these two temperatures. Okay, so that is easy to find. Find Vmin. So in here, we're going to write the equations for this one. I know, for example, that, what is it? Pmin times Vmax is equal to this temperature, NR TH. Okay, H. Actually, I probably should address it with the indices in here. It's this point that I'm looking at. Pressure sorry, Pmin. What is this? I'm sorry, pressure, Pmax, MA. Pmax times Vmin. Okay, is equal to nRTH, this point in here. Also, I know, again, if you run out of space, please use an extra paper in here. I know also this point, Pmin times Vmin is equal to nRTC. Pmin times Vmin is equal to nR T underscore C. Okay, I know also Pmin times Vmax is equal to nRT underscore hat, because this two belong to an isothermal. Okay, what else do I need? Do I know in here? So from here, we're supposed to find Vmin, because Vmin is not given to us. Vmin, I can use this equation divided by this equation. Is going to be Vmax. NR cancels the NR. Is going to be the ratio of TCs over TH, which is tau, by the way. Okay. So Vmin is going to be Vmax divided by tau. Okay. It's going to be what is it? Max divided by tau. Okay. Because it's going to involve TC over T hat, and TC over T hat is 1 over tau. Okay. So this is an expression in here. What is the ratio in here of Vmin over Vmax? If I take Vmin over Vmax, from this expression, actually it's 1 over tau. Okay. And the number of moles, I can use one of the equations that has everything I know. Okay. Since Pmin is given, and Vmax is given, here it is, and TH is given, and R is given, so this is going to be Pmin times Vmax divided by RTH. So this is going to be P underscore min times V underscore max divided by, if you wish, R T underscore H. Okay, because this point in here, this point, Vmax is given. Here is, they said Vmax is given. The Pmin is given. Here is Pmin is given. And also, what else? And TH is given, and R is constant. So we should be able to use that to find what that expression is. There is another thing that they want us to find, and that is Pmax. Pmax in this case is going to be given by taking the ratio, for example, of this expression. Okay, Vmin and the first two equations. If I take this equation over that equation, the min and the max, they will the volumes, they will cancel. So it'll be left with Pmax over Pmin equal to nRTH over nRTC, and TH and TC are given. And the ratio is actually tau in here. So it's going to be Pmin times tau. Okay. The last thing I need is to multiply this number by Avogadro's number, and we're in business, okay? We have found the number of moles in here. So we're going to say it's Na times that number that you're looking at in there. So it's N underscore A times Pmin, which is given, times Vmax, which is given, divided by R times T underscore H. This part now is plug in the numbers. Use this formula, because now we have tau. Tau is just a ratio of T hat over TH. So all I have to do is multiply it by Pmin, and Pmin is this number. So 1.33 times this number. I'm going to plug the number in here, and it's going to be the same units as this one. So it's going to be joules per cubic centimeter. Okay. Vmin. For Vmin, I have Vmax, which is 1,000 divided by tau, and tau is 1.33. So I have to take 1,000 divided by 1.33 and plug it in here. Okay. Vmax. Vmax is equal to 1 over, I'm sorry, first of all, rho. Rho is 1 over tau. So the invert of this number, which is 0.75. Is it? 3 over 4? Yeah, 3 over 4 is 0.75. So that is basically, did I make a mistake in here? I think I did. Vmax over Vmin. That cannot be correct. Vmax is nRTH. Yeah, okay, it's 1 over, so it's tau actually, I'm sorry. So this is wrong, okay? So this ratio actually is going to be tau. It's 1.333, okay? Because if you're careful, you have to be careful in here because you have Vmax over Vmin is equal to TH over TC, which is tau, okay? And that is the same thing as the ratio rho, okay? So that is going to be, because it cannot be less than 1. You cannot expand in volume and have it less than 1. It has to be more than 1, okay? So this is not really a great engine in terms of compression ratio. Usually compression ratio is several order of magnitude, not like this one, 1.3, barely basically expanded, okay? N, the number of moles. Hopefully didn't make a mistake in here. So we have Pmin, here it is. We have Vmax, which is this one, okay? Multiply the two by themselves and divided by R, which is 8.384, and divided by also T hot, which is 400 Kelvin, and you're going to find the number of moles. Please use the SI units in here, okay? But since you have a cubic centimeter and you have a cubic centimeter, so the cubic centimeter will cancel the cubic centimeter and you're in SI actually, okay? So this number will be fine. So we're going to get a number of moles, which is 1,000 times 0.1, that's 100, times divided by R, which is 8.3, I don't know. It's roughly about 12 or 15 or something like that, something. Divided by 300 by T hot, which is 400. So we're going to get a tiny number in here. And now the actual number is this Na, the Avogadro's number, times this number. And now you have the actual number of gas molecules in here. Does this table make sense to you for this particular example?
Yeah, you made that very clear.
Very good. So think of the rest of the engines. This one, though, you have, this is the isothermal. It's like flipped, example 1, except flipped, okay? So the relationships are different that you're going to be writing in here, okay? Example 3. We're going to go to the second section. You have in here an adiabat. That means T hot Vmin to the power gamma minus 1 is equal to, so there is a relationship in here that I need in here, T hot times V, T underscore hot, I'm sorry, underscore H, times V underscore min to the power, open parentheses, gamma minus 1. Minus 1. I'm sorry, we can't do any more than that in here, okay? Equals to, so this point is equal to this point in here, which is TW. I don't know what that temperature is, so they called it TW. So it's TW. It's an intermediary temperature somewhere in there, okay? Times the volume Vmax to the power, open parentheses, gamma minus 1. Okay, so this is one relationship. In addition to Pmax times Vmin equals to this point, nR T hot, in addition to Pmin times Vmin is equal to nRTC, this point, in addition to Pmin times Vmax equals to nRTW. This point, okay, this point in the diagram. So those are what we have in this process, okay? If you want to, you actually, and I did not do it for the previous example, you can find delta U and delta Q and all of that. In this case, through this stage of the cycle, okay? What we know also is that Q or delta U, I'm gonna use del U for delta U, is equal to N CV T hot minus T cold. It's this process, this isochoric process. From T hot to T cold, I'm gonna write del U. Of course, by the way, here, in this case, also, comma, W is equal to 0, and Q is equal to to del U. Okay, for this process. For this process, going through the adiabatic expansion, we have, and I have to write space in here. That's why probably you need to have an additional piece of paper. Del U is equal to NC underscore V, the temperature, the final temperature TW minus T hot. Okay, so that is the amount of work, and that is equal to a negative W, by the way, because Q is equal to 0 here. Okay, for this section in here. And finally, for this section, which is an isobaric process from temperature TW to TC, so what we have in this case, del U, which is equal to NCV times the final temperature, which is TC, minus the initial temperature, which is TW, and then also W, the work in this case, is equal to the way it's defined in here with a plus sign. So we're going to take it P, which is Pmin, times the final volume, which is Vmin, minus the initial volume, which is Vmax. Okay. And finally, the temperature in this case, the heat in this case is NCP times the final temperature, which is TC, minus the initial temperature is TTW. Oops, TW. Okay, so those are the equations we will need for this whole thing. Then we're going to be answering these questions. What is given in this cycle? We're given Vmax, we're given T hot, we're given T cold. We don't know what TW is. We can find it. Okay, we're given Pmin. We're not sure what Pmax is, but we should be able to find it from these equations, basically. And we're given gamma. Actually, gamma is given in here. Okay, and we're supposed to find the rest of it. Tau is known from here. Tau is actually equal to TH over TC. And it's going to be the same number throughout the entire process, okay? For all of the examples, 1.33333, okay? So 4 over 3, 400 over 300, okay? So you're supposed to use these algebraic equations in here to find everything you're supposed to find for your processes. Usually it's just these equations in here. But again, at some point, you're going to be finding the other equations are actually needed for the second page that I didn't show you yet, and I'm going to show you that. So do you guys understand how you're supposed to be working these processes? Good?
Yeah, kind of.
Okay. Please, if you're stuck somewhere, don't be stuck. Okay, let me know. Okay, we need to make this thing move along. So I'm just dealing with the first table. We're going to do the second table because that's part of the process in here. This is similar to the previous one, to example 3, except that the processes are a little bit rearranged differently in here. And this is Now, different process. This is kind of a different one. So this is at constant temperature. This is at constant pressure. And this is at constant entropy or adiabatic process. So the relationships are different in here. So the relationships in here are Vmin. Let's write it down. P underscore max times V underscore min is equal to nRT hot. For this point. For this point, the second point, P underscore min times V underscore max. Okay, this point is going to be the same thing, nR T hot, because it's an isothermal process. Temperature is the same, hot T hot. Okay, now for this intermediary point in here, okay, we have P underscore min times V underscore mid, the middle volume, is equal to nRT underscore cold. And this is your 300 Kelvin, by the way. It's sitting in here. Okay. Okay. So these are the some of the relationship. We know also that this is an adiabat. So P underscore min times V underscore mid to the power gamma is equal to P underscore max times V underscore min to the power gamma. This point and this point are part of an adiabat. So this relationship is correct for them. As a matter of fact, we have a relationship between T hot and T cold because of that point too. So we know that T cold at this point times V mid to the power, open parentheses, gamma minus 1 is equal to this point on the diagram, which is T underscore hot times V underscore min to the power gamma minus 1. Okay. In addition to the PV equal to nRTs. Okay. In addition to the energies. In here, delta U is equal to 0 in this plus, and Q is equal to W, and it's equal to nRTH times the log of V max over V min. In this case, Q is equal to 0. And in this case, Q is equal to 0, but W and delta U is equal to minus W, which is equal to NCV, T hot minus T cold. And there is actually another one in here. Excuse me 1 second. Somebody is knocking on the door in here. Let me pause this one quickly here with you guys. Stop sharing, see exactly what's going on. Sorry about the disruption. Anyway, so continue with this one in here. There is another step in here that is actually an expansion at constant pressure. Okay, let me share with you screen. I'm sorry. I probably should do that, shouldn't I? So there is actually in here an isobaric process. So in here, in this case, delta U is equal to NCV delta T. Delta Q is equal to NCP delta T. And the work is going to be P, which is P min, times the final volume, which is V mid, minus the initial volume, which is V max. So all of these identities. Now solve all of them to find all of these intermediary values and everything else, okay? Similar to the example we did before. Again, if you have difficulty and you chose, regardless, you have to understand this process as part of your exam preparation. And I know we didn't do the second one, we're going to come to the second table, but I'm going through all 8 of them first through the first table, okay? Because we need these relationships to finish that. Now here is a process that is similar to the first process, process number 5, exception that it's a little bit different. The other one had the adiabatic in here and the isothermal in here, and it had the isobaric process in the bottom, now the isobaric in the top. So the relationships are identical, except the midpoints and the T hot and all of that has moved a little bit. So we're gonna do that too for the process number 6, process number 7. Process number 7 is similar to that process, except it does not really involve an isobaric process. An isobaric process involves an isochoric process, which is a little simpler because that involves W is equal to 0 here, which means that NCV delta T is exactly true for both delta U and also Q. And again, I have all of this relationship because this is constant entropy, which means Q is equal to 0. This is an isothermal because TC, and this is an isobaric process, okay? So you have a bunch of relationships in here, and you have to solve for P max and P min, and similar to what we did before, and this is what you were given, okay? Tau is just the ratio of the 2 temperatures. Since you're given that, so you can use that in your formulas everywhere in here. And now you have a number for tau, so you should be able to solve for all of these equations. And the last one should be a similar process, except now the isochoric process has shifted from one location to another, and the isothermal was in the bottom, now it's in the top, and the isentropic or the adiabatic process moves from the top to the bottom, and it's similar to that one. So I hope that all of these processes, you're going to go through at least the first table. The second table, let me go back through the first example that we did, basically, and hopefully, no, what is it? Table 1. So we did this, so I didn't finish the numbers, so I'm hoping that you guys will finish the numbers for this part. So let's go to the second table. Now the second table looks at the different processes. There is a constant pressure process. What is the constant pressure process? The constant pressure process is this one. This is happening at P min. So at P min, I need to write delta U, I need to write delta Q, and I need to write delta U, W, okay? I need to also look at the second process happening at V min. This is the isochoric process. So again, this is where V min is, constant. So this is the isochoric process. I need to find delta U, I need to find delta Q, or Q actually, and I need to find delta W. And each time I'm going to take this value minus this value. Does it equal to the delta U? If it is, I'm going to say yes in here. So most of the time you're going to say yes in here, yes in here, yes in here, unless something went wrong in the calculation, which I need to be aware of. This is the numerical values. This is the same thing. So this is symbolic manipulation, and this is actually plugging the numbers that you have in the previous table. So this is the first part of that table is just following this one. The second part of the two, where you have the values, you're going to be in here with the values. So the first one is just the formulas. So let's do P min. We know that P min is constant, and the change in the work in this case is going to be N R, going to be the final temperature, I'm sorry, and CV. The final temperature is T cold, and the initial temperature is T hot. So it's T cold minus T hot. Okay. This one, constant pressure, so it's NCP times T cold minus T hot. Okay. This one, okay, is going to be it's going to be P min. This is the temperature where this, the pressure where this is happening. V, I have to go back into the table to see what. So this Vmin minus Vmax. Vmin minus Vmax. Okay, I have Vmax. It's given. I don't have Vmin. I have Vmin as being Vmax over tau. So I need to replace this one by Vmax over tau. Okay, Ma over tau. Okay. I have T cold, I have T hot. Do I have Cp in here? We have gamma, and gamma is Cv over times Cp is gamma times Cv. So this is gamma times Cv n gamma. So make spaces, please, otherwise this thing will run to each other, okay? Okay, and this one is NCV times that, okay? So now Vmax times Pmin is equal to NR. Okay, let's go back into the expression here. Vmax, oh, I'm sorry, what is it? Pmin times Vmax, Vmin times Vmax. Pmin times Vmax is NRTH. So this is NRTH. So this is NRTH. So I need to do the calculation in here. I will find that it's equal to NRTH divided by tau, and tau is TH divided by TC. So this is going to be NRTC. So it's going to take the NR out, and it's going to be TC left in here. And if I'm careful enough in here, actually, this is going to be T hot. I do the algebra in terms of what's given, not in terms of something else that is not given, okay? Now, if I take this number, subtract from this one, would I get this one? That is the question. Obviously, you need to use equation 6 in here, okay? You can leave this one if you want to as NCP. And take this one minus this one. I think, what is it? TC minus TH. So you're going to CP basically minus CR. Is it equal to CV? And it is. So if you take advantage of equation 6, you're going to get yes in here. Okay. You're going to do the same thing in here for Vmin. During this process, you're going to find that W is equal to 0. So this part is easy. And in this case, it's NCV delta T. And delta T is from T cold to T hot. So the difference is T hot minus T cold. And this is the same thing, by the way. It's going to be NCV. It's always that. From the initial temperature, which is T cold, to the final temperature. So it's the final minus initial. And that's going to give me this expression. Is it true that this number minus that is equal to this one? Obviously, yes. Now, at T hot, there is it's an isothermal process, so there is no change in the energy. Okay, and it's going to be N R T underscore hot ln the ratio in here of Vmax over Vmin. If you look at this expression, Vmax over Vmin is tau. So the ratio is going to be tau in here, ln of tau. And this is the same thing. It's going to be nr T underscore H times ln of tau. Is it true that this number minus this number is going to be 0? And the answer is obviously yes. Come on. This thing is frozen for me. Okay. Is yes. It's not writing anymore. Okay, good. Now I need to add these numbers in here and check that they add up to 0. Okay. TC cancels TC, TH cancels the TH, and NCV is the same. So, and this is 0, so it has to add up to 0. So why is it that way? So I'm going to say yes in here, by the way. And it's very small in here because of the fact that doesn't see. Okay, good. Okay. I need to, so when you add these numbers, they should add up to 0. Now I need to add the W's in here and see how much work I have in here. Okay, it's going to be this number plus 0 plus this number. That is going to be the W net in this case. Obviously, this is negative and this is positive. So I have to be careful in here between that is the W net. Now, this is the Qn. The hot during the heat that is that you get is during this cycle. So this is Q hot, and this is the time when you get rid of the heat in this case. Okay. I'm sorry. What am I talking about? Oh, I'm sorry. I'm looking into the work. That's not nonsense. This is the cycle in here. Okay. So we're getting heat actually. So we're going from TC. This is where we get rid of the heat. No, this is where we're getting hotter. Okay. We're getting net heat in here. We're getting less in temperature from T hot to T cold in this case. And let me look at the graph again here. So in here, we're getting heat during this stage. And we're getting colder and we're getting heat. So we're getting heat in here and here. So that is actually Q hot is the sum of these two heats. It's NCP delta T plus the Q, which is the NR, NR T hot, ln of that tau ratio. Because Q is positive in here and Q is positive. You have to add the two of them. That is the Qn. And the Q hot is happening, QC is happening only in this stage. So in this case, the Qn will be the sum of these two quantities. That is happening here and in here. That is the Q hot. And this is the Qn. I mean, the Qn, I'm getting confused about the notation. This is the Qn, which is the Q hot. And this is the QC or the Q out. Okay. And then you're supposed to check if it is true that indeed this is the case that you're going to end up with. Because don't forget that CP plus CV in this case, or minus CV in this case, because you have the signs backward, is equal to R. So indeed, if you do the algebra, it's going to be that this Qn, which is the sum of this quantity plus this quantity, is going to be this quantity, okay? This quantity for Qn minus this quantity is going to be exactly the work in this case, okay? Follow the relationship in here. You're going to need equation 6 again in here because you have CP and CV in here that you need to have them in there, okay? And you will check yes on this one in here. And this is the efficiency formula. Now, when it comes to numbers, you have everything in here. You have calculated everything from the previous table. You know what Pmax is, you know what Vmin is, you know what V rho is. You know what n is, you know what n is, and you have the other values that are you don't see them in there. So technically, you have no excuse not to calculate everything in this case in here, because you will need n, the number of moles. You need CV, because you know what gamma is. So you can find what CV is. You can find what as a matter of fact, it's not a good idea to leave it in terms of CV in here. Express it in terms of question 1. Remember question 1? Where is it? Question 1. This question. Express things in terms of R and gamma. Since gamma is given, use that to your advantage to find CV and CP. So that when you are doing the numbers in here, since gamma is given to be 1.4, okay? Don't leave it as is in here in terms of CV and CP and all of that, okay? Use it in terms of gamma, because that's gamma what is given in here. So you can use question 1 to find everything else in here. It's not asked in here, but since you're doing the energies, you will need that CV and that CP in here. So you need all of these calculations in here, at least for this part. So technically, you should find a number in here in joules. Should find a number in here in joules, a number in joules, and when you subtract this from that, when you subtract W from Q, you're going to find this number. And you're going to check all of these things in here. We went an hour and a half just through this lab. Obviously, this is a lengthy calculation. Needs extreme focus, okay? The fact that they changed the deadline when this thing is due does not excuse you from not starting it as soon as possible. The reason why I'm saying that is it has a lot of bearing in terms of your exam. Yes, the lab is not due until after the exam. So, but you need to understand of all of this inner workings and this gamma and CV and CP and R and Q and W and all of these things. It is outstanding if I see you guys working together. So this is something where cooperation is of the utmost, okay? Working with a partner will give you that feedback. And when we do this in the actual lab, this is part of the lab activity that you actually do in the actual lab. Not because we are online, I'm giving you these engines and you do them. Even if we are in lab, this is still a lab activity that you guys do in a lab, not a homework problem, not a recitation issue. This is an issue where you sit down and work out the details of it to have an understanding of calculations and how to calculate these things, okay? Does this make sense in principle? I know when you go through it, you're gonna have a little bit of a, you need to be of the utmost focus, and you can go through it. You can actually survive this whole 8 processes. Does this make sense? Once you write your equations, the key thing is with that table in there, where it says equations, okay? Once you fill out the equations, and you don't miss a thing, just because it's an isothermal process, the temperature is same. So PV equal to nRT on one side is the same PV equal to nRT from the other side. So I have connections between the volumes and all of that. If I'm dealing with an adiabatic process, then PV to the power gamma on one side is PV to the power gamma on the other side, or TV to the power gamma minus 1 on one side is TV to the power gamma minus 1 on the other side. And then I go through the same process, okay? If I have an isobaric process, then in this case, it's a little bit more work because delta U is always NCV delta T. And Q in this case is NCP delta T. And the work is P times delta V because P is constant now in an isobaric process. In an isochoric process though, W is 0, that's good. But then delta U and Q are the same and they both of them are equal to NCP delta T, okay? And this is basically of how this thing is, just this 4 cycles basically mixed together in this different 8 engines. Then obviously, let me finish the lab because we didn't really finish the lab. There is another part to it. So once we go through all of this and pick up our 2, which really is pick and choose. We're going through the entropy now, okay? And this we did actually in lecture 2. In the case of, again, the isothermal process, we saw this one, nRT ln, that's the Q. So you divide that by T and you cancel the T and it's going to, because T is constant in an isothermal process. In an isochoric process, Q is then equal to NCV delta T, and you integrate that expression is going to involve the natural log. And then the same thing for an isobaric process, except instead of CP, you're dealing with CV. And in centropic process, this is an adiabatic process. In this case, the entropy doesn't change, okay, because of the fact that there is no exchange of heat. Okay, so the S net is positive. So show that delta S is equal to 0 for the Carnot cycle. And we did that in lecture, actually. That was the example we did in lecture. So hopefully you can go through it and do that. And this is your conclusion. Does this lab make sense to you guys theoretically, at least?
Yeah, thanks for going over it so much.
Okay, no problem. Listen, guys. I'm going to be turning off. First of all, I'm going to stop the recording. I'm going to turn off my camera. I'm going to mute my sound. If you guys choose to hang around, I'm here. Just call me in. And give me about half a minute or so. I know we still have about an hour and a half for lab, basically, before it's over. So if you choose to stick around, that's fine. If you choose to leave, that is fine. But please take it seriously, and I cannot emphasize how important this is. This is really the culmination of the first half of this class. Okay? This is the climax of the first half of the class. Good. Oops, I'm going to stop recording.